All right, so this is the problem, and I understand it now. It's cool. And I'm doing it two ways. One way is with a system where it's just these things, and the other way is the system with everything. Okay, so it's gonna be Q2 over, this is the initial, so it's gonna be D plus L. Okay, but then it's gonna be plus 1/2 mv final squared. So then you can just move this over, and it's the exact same answer. Actually, they're about the same amount of work. Okay, so that one's chill. Okay. So let's make our notes. So I got my notes on all my problems. So I think was this 90? Bro, this one, okay, when I was in the library, this one pissed me off. Actually, this one pissed me off too. I want to redo this one maybe. Should I redo this one? Yeah. All right, I'm gonna do it on my whiteboard. I brought my whiteboard in. You're not gonna see that. Okay, but I think I know the problem, and I want to do it. Actually, let's see. You're just gonna watch me write something randomly. Actually, it's probably better if you see the problem, because then you can do it by yourself. So you got initial. It's called beta. L L minus Q. we have the potential energy here. So this potential energy is going to be delta UE. So first off, UE initial will be just, it's just going to be a K minus K Q1, Q2 over the radius between them, which is going to be R. The distance between them. Okay, but then the final is unknown. How do we know that? The final is, but the charges UEF is equal to 0 because charges eliminate. All right, so that's good. So now this is just going to be UEF minus UEI equal to K Q1 Q2. Or so this is actually going to be, wait, how did I do this? This is going to be like this, but it's going to be just K minus Q squared. So it's going to be just K Q squared over Ri. So that's good. We figured that out. So that's done. Boom. Now we need the delta of gravity. So the change in gravity is going to be, these both are by symmetry, because they're both going to go up and down by the same amount. So that means that we're going to have m before the mass of the things times gravity times y final minus y initial. And this is going to be times 2. So this is equal to the UGs. Okay, so now we can write our full expression, which is going to be, 0 is equal to KQ squared over RI plus 2mg times YF. So we need to figure out what YF and Y initial. Y initial, if this is the tricky part. Is you do this. This is just say Y equals 0. So then this height will be L minus L cos theta. So this is going to be L minus L cos alpha minus L minus L cos theta. So this is going to be equal to 2mgl cos theta minus cos alpha. Okay, what we're trying to find is alpha. But now what is Ri? We need to tack, because Ri equals 2 L sine theta. Okay, so now we want to find alpha. So we're going to have minus k q squared over 2L sine theta. Theta, okay, is equal to, I'm going to divide by this. This is actually going to be 4L squared sine theta mg. Plus cos theta. I think that's pretty much it. And just take cos. Wait, hold on. No, I haven't eaten yet. I'm just gonna eat that stuff that I. main part of the freaking physics. All right, that was a good one. I like this one a lot now. Let's see what the answer was. Yeah, this, and then here, I messed up a minus sign, but that's pretty minimal. Oh, and then determining whether that's the other thing. One thing I don't understand is let's see, is it this one? Yeah. Because like they do. If you literally try to bring, oh, but I don't think that there is a radius on these balls. But presumably, okay, they're small, but they have some radius, so it doesn't really hit there. But when they hit, okay. But anyways, the important part is the final potential electric potential energy is zero, but initially it was negative. That means that energy had to be used to bring that to zero potential. That's the whole part of that's the whole problem, really. Is understanding that conceptual. Oh, it feels good to be at home with my whiteboard, bro. Okay. So what was this one? 90. Oh, this is a good one. Great work energy problem that can be done with multiple systems. 23. Okay, come on, no looking, no looking, no looking. A bead of mass. Oh wait, I know this one, bro. This is a classic. A bead of mass m and charge minus q is constrained to move along the x-axis by a frictionless wire in the presence of a fixed charge distribution as shown in the diagram. All right, so we have 2-point charges, plus q1 plus q2, and they're equal. So that kind of simplifies some of this stuff. Find the period of the bead's oscillation about the origin. All right, this one's easy. I feel like I've done this a number of times, but let's just do it. minus q e equals to x. So then r1 x minus d, r2 x d minus. Alright, so that's good. So now we're going to have k q or kq1 over r squared. Or no, we're going to we want this so that we can take the whole vector x minus d k plus k cubed 2 over r cubed of x d. Add these together, we're going to get, oh, but these magnitude, these are, so we're going to get k cubed over r 3 times 2x 0 2 k cubed x over this is the electric field. So now what we want to do is find the force. So F equals QE. So then it's going to be little minus Q. So F is equal to minus 2K Q X over F3 X. Okay, but this goes. So I'm going to get equal to so okay, so then okay. Low-key that problem is so easy at this point. Yeah. I mean this problem is like at this point this is so easy. Just okay, so let's just keep going. 76. Ooh, okay. Say that a dielectric sphere of uniform charge density rho has a negligibly small, okay, so a small point of value plus q and mass m can freely move through. If the point charge is at rest at the center of the sphere, but then given a small nudge, it will accelerate to the surface along the shaft. Find the speed of the point charge when it gets to the surface of the sphere. Okay, so this one is just going to be Gauss's law for the electric field inside the thing. And then once you have the electric field inside there, you can compute with a line integral the delta V. Then you can find the work done on the system of that point charge to move it to distance r away. Now that you have the work done, you know that since the system is just Q, there's no potential energy. It's just, and it's initially at rest, so it's just the final kinetic energy is equal to the work. So that's it. This one is so. Oh wait. Oh, and he gave you that the electric field in the. I mean, bro, this problem is like. All right, I'm not even gonna use that. I'm just gonna do Gauss's law because it's easy. Let me see if I'm missing anything. Find the speed of the point charge when it gets to the surface. For simplicity, assume that the initial kinetic energy is 0. Man, this is an easy one, bro. KEI 0, 1 half MVF squared is equal to the work minus Q delta V. What is that? This is going to be equal to minus mu E L. Okay, so E. Okay, so E of R. We're going to have flux E dot dA is equal to rho times 4/3 pi r cubed over epsilon naught. Okay, so we're going to get radial sphere sin E times 4 pi r squared is equal to 4 rho pi r cubed over 4 pi. Okay, so now we have the. So now we just need to do delta V is equal to minus the integral of rho r over 3 epsilon naught r hat dot dr r hat. These cancel. Now I'm going to get minus rho over 3 epsilon naught integrated and this is going to be from the path data to 0 to 4. That's a good R to all right, so the change in potential is negative. That's good. Okay, so then work is equal to minus Q times minus R. At this point, I can do this problem in my sleep. Wait. Wait, what happened? Q. Oh, I missed the. Oh, I forgot the. I forgot the R over 2. That's okay. But I got this. I don't know what all this is about. No, he takes the R out. I feel like there should be like a. Where did epsilon not go? Anyways, this is the answer. This is the easiest part. At that point, it's like, okay. You're not being great on your algebra. El Clasico. Work energy. Actually so easy. Okay, 42. Find the electric field at the indicated point in the diagram. Use the coordinate system given. A formable vector treatment is required. Okay, I need to get a new pen because this pen is totally dying on me. All right, so this is just integral d. Bro. Okay, I think I can do this. X. Okay, so length L, Q, okay, P, just X. Okay, this is the class. Okay, so wrong. Q, origin. Okay, so we're gonna have DQ here. Okay, so this distance, this is going to be y. So x0 minus y equal to x y. So e equal to integral dE by integral superposition. You can add up all. Okay, so this is going to equal to integral k dq over so r equal to r q. Okay, so dq. Okay, so now we have equal to the integral of k lambda dy with 0 to L x. Okay, so then now we're going to separate this up. Integral 1 is equal to 0 to L. I think we can pull out k length, so this is going to be equal to k lambda All right, just to go through these fast, I'm like getting tired of just doing all the integrals. So he didn't even do the integrals. He just left it like this, which is great. Okay. Easy. I left lambda in there, but I mean, come on. Like, how important is leaving lambda in there? All right. So this is like it's like 105. That's really easy. Ooh, okay. The simplest atom has a stationary nucleus of plus Q charge, the proton, and a negative charge, an electron of minus Q, and a mass m, like the whole thing, that is in circular Newtonian subtriple. Yeah, I need a bro. If I get a v squared over r, I'm gonna be pissed. Is in a circular Newtonian orbit about the proton of final given radius RF. Find the work done by an external applied force to create this atom. Ooh, bro, this is gonna hit me. This one's hard. Find the work done by an external applied force to create this atom from an initial distance between the electron and proton of infinity and initial speed 0. Okay, so I think what we need to do is we basically need to find the energy of the system. And once you find the energy of the system, that's how much work it is. So what you're going to have is you're going to have a change in potential energy, which is going to be, the change in potential energy is going to be negative. Because you got to think about when you have a dipole, pulling it apart is increasing the potential energy because it's like a spring that wants to come back together. But so when you bring it close together, then you're like letting the spring kind of come back together. Okay. So there's gonna be that. Then you're gonna have the kinetic energy of this. So I think I'm gonna take the system to be both particles. So then we're gonna have a potential energy, but then the work done. Ooh, actually, if I take the system to just be Q minus the electron, hold this fixed, which is fine. RF is given. Okay, so we know. Why is that important? V squared over R. Okay, because in F equals MA, you can get F equals V squared over R. So then you can get the force required. This is a crazy one. Right, which one is this one? 66. So you have so what mass is it? The electron has mass? Yeah, so the electron has mass. The nucleus doesn't have any mass. Well, in this problem because it's fixed. So so we can get the force. Oh, this problem is hard, dude. Okay, so like one thing is I can just figure out the work required to bring minus Q to RF. That I can do. That will be basically the change in potential energy if you took it to be both particles. Okay, KEI could be 0, and KEF has to be the kinetic energy, the velocity. So, okay, wait, actually, we could just find the velocity. So we could get, but what is F? I don't know what F is. Find the work done by an external applied force to create this atom from an initial distance between the electron and proton of infinity, and initial speed 0. Okay. All right, so let's just decide. So we have work is equal to, okay, I know the problem. I'm going to go do it on the whiteboard. Is this the right one? We have this thing. This thing has an acceleration. So minus Q is fixed. So, okay. So that means that yeah. Okay, so now we have there's going to be a change in KE plus minus this is 0. This is going to change. So it's with the k e pi equals 0. Okay, then we're going to plus delta u e. Just find the energy of the system. That has to be the amount of work. Okay, so this is going to be 1 half mv. Acceleration. Okay, so he took the system to be both. Okay, he did that. He did this. He did that. He did that. He did that. VF what given? Okay, I got to right here. But then minus kq squared over rf plus 1 half. What is this? F equals ma, system equals mass. Okay, so he's saying that the Coulomb force, is that what he's saying? That the Coulomb force is equal to, bro, see, that is the part that I did not see coming. Is that this force mv squared over r, this is the other force. I knew there was going to be something to that. Okay, so that those forces need to cancel out. That's the main thing. Crucially, you have this, this thing with an acceleration that points inwards, I think. So this is going to be the F centripetal. That's accelerating it forward. And then this, wait, no. Hold on. Yeah, we have F equals ma. The acceleration is not 0. Oh, yeah, so we just have the k q squared over rf squared is equal to mass times acceleration, which is going to be mv squared over rf. So this goes away, this goes away. So what are we trying to find, though? We're trying to find vf. Okay. Or really, we only have to find vf squared. So then vf squared is equal to kq squared over mrf. Okay. Now that we have this, I think I got it. Okay. We have this. Yeah. The main thing is definitely seeing that you have to apply F equals ma on a separate system to figure out what the work applied is. So it actually takes negative work to make the atom. That's crazy. Okay, this is a really good one. You need to apply work energy, then F equals ma to balance centripetal and Coulomb force. That's a good one. All right, 49. A rod of length Q, or a rod of charge Q and length L is pivoted about one end only. The rod is immersed in an external uniform field, making an angle theta. Find the magnitude of the torque on the rod from the external. Okay, El Clasico torque problem. So, okay, so yeah. Okay, so we need d tau, d tau, d f. Okay, so tau equals integral r cross df. We cross q e q. This thing that r has to equal to s cos s sine. Okay. So what does that mean though? That means that dq. This is the. So this is r, right? So we found r. Okay. Now we need to find dq. So it's little dq to be over ds equals to like this is long thing. So dq is equal to lambda. Oh yeah, that's the. Okay, so here we're going to say. So now we can take I. This is going to be s cos s sine. And this is going to be e and then ds. QL. Yeah, QLE over 2. QLE sine theta over 2. Okay. Easy, bro. Okay. The simplest integral d tau torque. Oh, fuck. When you see that. A bathroom. Okay, wait. Actually, wait, hold on. I want to see. Redo. A bathroom scale is that device a person stands on to read his or her weight if the bathroom is not accelerating. However, we know that the bathroom scale actually measure the normal force between the person and the floor. Say that a charged parallel plate capacitor of given A, so it has a magnitude. I think I just what does he do? Here's Gauss's law. He finds the E field. Then he does um QE sigma A E. Now E from one plate. To find the force, what does he do? Wait, let's close all these other ones. Um, by the other plate. That's the magnitude of the attractive force between the plates. Okay. So we just need to find the force. Okay, fine. That's fine. All right. There's no gravity in this problem. A given uniform electric field exists in the region of interest. Find the final speed of the charge after it has traveled a horizontal distance of L. The charge is injected into the region with a given initial velocity perpendicular to E as shown in the diagram. Find the final speed of the charge. Okay. All right. So, oh, this is a good one. This is like that. Oh, I got to do these. Okay. This is like the one that says find the time or something. It's kinematics. Okay, so first off, we need to find the time. So VIX times time is equal to L. So T is equal to V L over V I. So this is the time that it takes. So now what we want to do is we want to find the acceleration. So we can find the force. So the first off, the electric field is just equal to, E J hat or something. And so the force is going to be F is equal to Q times E. And then VIY is equal to 0. There's no initial vertical velocity or acceleration. Okay, so this is the, and it's just QE is the force on that body. So this is equal to the mass times the acceleration. So the acceleration is going to be QE over M. So now, because none of this doesn't change, all constant. So then that means that we can find, 1/2 QE over M times T squared, which T squared is actually going to be L squared over VI squared, is equal to something. Is it going to be equal to Y? Because it's going to be Y0 plus VYT. These are both 0. So I think it's just going to be QEL squared over 2MVI squared. Wait, but VIX squared. I missed something. Oh, wait, it said find the velocity. Oh, wait, find the final velocity. Okay, so this is the distance traveled. Uh, wait, VFY is equal to VIY plus AT. Okay, I didn't know that equation. So that means that and VF is equal to the square root of V, the norm of, okay, fine, of this is equal to the square root of VFY squared plus VI squared. So that's the final, oh, it said find the, there's no gravity in this problem. A given uniform field. Find the final speed. Oh, not find the final y direction speed. You got to read the problem. Okay. Okay, so VFY. All right, so we found this. So this is, so A is just equal to QE over M. So this is, so AT, so then, so VFY is equal to, this is 0, QEL over MVI. Okay, I did that. Um, okay, then he does F equals MA, QE. Okay, I did that. So VF. Okay. So this, okay, so this is, so the way that you find, I think I need a new one. They both have to be constant, I think. Okay, so But I think then I wanted to retry, not this one. It's this one? No, no. Not that. It's not Gauss's law problem. This. Oh, it's this. E field 1. Okay, we gotta redo this one. E field 1, this is a good one. Okay, E field 1 is up next. Okay, so let's just see. Did we finish this? I'm shaky on those kinematics problems. I'm shaky on the kinematics. Okay, all right, let's do this. This is E field 1. An electrode of charge minus E and mass M has an initial, because this is all plus charge. This is a minus Q with mass M, and it has a VI is equal to VI 0. The enters two plates is shown there, and what voltage across the plates. Okay, so find the delta V such that, so this is going to be P equal to LD. Okay, so the first thing we can do is we want to find the time. So VI T is equal to L. T is equal to L over VI. We must move D amount J hat in L over VI time. Okay, so now how do we uh, think about this? The work it takes. Okay, so what can we do? We can find the work it takes. So this is going to be equal to D. This. Okay, so Okay, I think I did this kind of a wacky way, but I believe that we should get delta V 2d squared V. I don't think this is right. 2. Oh, actually, I got it, except for I think there should be a d squared in here. Or I got a d squared. Okay, let me write down mine. I think I probably have it. Oh, actually, okay, wait. Um, Wait, actually, did he say? 2d2 vi2 m over ql2. Yeah, let's go to the next one while we wait. Because I feel like what did I do? I said we have F equals MA. We need. Okay, let's keep going. I want some work energy. I like the work energy. All right. Oh, torque? Is this a torque? A uniformly charged rod of negligible mass is free to rotate about the fixed pivot of the origin. A fixed point charge Q is located at a vertical distance below the pivot of D. Ooh, this is a hard torque one. Holy cow. Uh, okay. Find the horizontal distance L from the pivot where a hanging mass M would be located such the angular acceleration of the rod would be 0. Okay, so first what we're going to do is we're going to find R, and R is just going to be the distance from the origin. So that's just going to be 0, y, 0. Then here we're going to have E, and E is going to be a weird vector, but E is going to be D, so DQ, E is going to be K, Q, KQ over D squared plus, oh, X squared. I said Y earlier, I meant X. D squared plus X squared. So that is going to be E. And then, but okay, but we're gonna have to do the full vector thing, but that's chill. All right, so I mean, the main thing that we want to do is we want to find the torque on this thing due to this point charge. Once we find that, then we know the mass, so we just need to find the position where this so okay, it's torque balance. I'm gonna do it. I'm gonna do it on the board, and then I'm gonna do it here. This problem was actually way harder than I thought it was going to be. Okay, this is L. This is D. This is Q. This has a big Q on it. And then we gotta find the position of this mass. Oh, wow. This problem is actually hard. These torque problems are problems that are long. Okay, so Bruh. These problems are so easy to mess up. Hold on, we gotta start over. So in this determinant I, J, K, we have EY is equal to KQ D over R cubed. But then EY times DQ is equal to KQ D lambda. It's like I should have noticed that there was never an integration variable and I just randomly introduced it. I think this just needs to be a lambda. There's a lambda here. Where did this D come from? Okay, so here lambda K Q D X. There's no X in here. I'm just memorizing the freaking problem. All right, we gotta do it one more time. Actually, is that wise? It's already 10. Oh boy. I just gotta remember. You gotta go slow on these torque problems. I actually write it out. It's like one. Um, the problem is that there was another torque problem. Let's see. Torque. Much torque. Great problem for torque. Very for the best torque problem yet. The simplicity. Okay, this one. So think about this one. Is okay if E is uniform, just do cross product. Okay, if the E is uniform, else use cos, or sine. Use trig. That's probably the best way to do it. Okay. Then for find dq. Okay, so then after you take the cross product, you actually got to integrate. Bro, torque problems are so annoying. I'm going to do it one more time. This is the last time. Okay, we have a pivot. the origin is the origin. Then we have a mass. Okay, then we have this point charge here, the distance d, this is L with Q, this is M. Okay, G. Okay, so we're going to have torque due to tension plus torque due to E is equal to 0. R cross Ft plus R E cross F E. But this requires integral d tau is equal to so okay, what are the steps? The steps are first find R. So RE is going to be equal to x 0, 0. Okay, now df is equal to E dq. E is going to be equal to k q R is equal to d squared plus x squared square rooted. This would be R hat. But EY is going to be equal to E cos theta j hat perpendicular. So then this is going to be equal to k q d over r cubed j hat. Now dq is going to be equal to okay, so now I think we're ready with our elements. So now we're going to have so we're going to have R E cross E dq is equal to R, this is going to be x 0, 0 cross 0, and this is going to be E dq is equal to k q d over r cubed j hat times lambda dx. Okay, so this is going to be pause torque. Okay, so then it's going to be d tau is equal to forgot the lambda again. That's nice. Okay, so now we can do u is equal to x2 plus d2. So we're going to get minus 1 over square root x squared plus d squared, valued at L0. So we're going to get 1 over d minus 1 over square L squared plus d squared. Okay, so then the final tau E is going to be equal to, so we did the integral, so we're good. We did the cross pronation, we're good. Okay, so it's going to be lambda K Q D K hat times 1 over D minus 1 over square root D squared plus L squared. Okay, so then this, so, tau 0 plus, this is going to be, so now it's going to be lambda, which would be Q over L K Q D times this. This is going to be G. Okay, I finally think I got it. L is equal to Q K Q D L M G boink. Let's go. These problems are crazy, dude. Torque is the killer. All right, let's keep going. Is that this one? Oh, this is a really nasty torque. Lesson is, if the field is uniform, don't worry about trig and just take cross. But because the problem is, if you end up with the displacement vector in E, actually, I'm trying to think. Let's just write it out. We have I, J, K. So the displacement was just X. Then EDQ. So we had the displacement R is equal to XD. But then E was KQ over R cubed times this whole vector XD. So, it's a full vector. And then, E dq is equal to KQ lambda dx over R cubed times the vector XD. So we just put XD, then we're going to get XD, K hat. This thing goes to 0. XD KQ lambda dx over R3. Actually, I think I just messed it up, and that's actually not that bad, because that's the right answer. Then you just integrate that. So it's just actually just, you know what? Oh, it's already 10, dude. I need like 40 more hours. I've actually looked at like a good amount of them at this point. I've looked at I skipped some of the like energy density and the capacitance ones, but okay, let's just rapid fire go through these. Okay, so 34. Using the coordinate system as shown in the diagram, find the electric field in the spherical hollow of the otherwise uniformly charged dielectric sphere given. Okay, he gives you the thing. So the thing is, Okay. That's pretty good. That's challenging. I forget how you do it, even if it's just on the line. Okay, that makes sense. We just did 30, right? No, we didn't do 30. Look. Wait, find the acceleration? There's no gravity, right? So first you find the E field, and then you do a dq over minus pi over 2 to pi over 2. But you need to, when you integrate the E to Q, you need to be careful because we need to do this one. Yeah. D plus, you can call this theta equal to 0. Sine, yeah, so it's sine, because it's at its maximum here. D plus sine theta. And that is going to be R. DS. Right, we need a DQ. RD theta. Two pi r over two. Okay. Pi r. Zero to pi. Yeah. So wait, so we found the force. We should divide by that. Okay. That's a pretty good one. That's a really good one. The positive charge of plus q of mass m is in between two charged infinite parallel plates of opposite charge but equal magnitude. Tied to a massless string of length L, where the other end of the string is held fixed. Say the charge is then let go from rest. Say the charge is then let go from rest at the bottom position. Find the speed of the charge as a function of the angle the string makes to the vertical. Whew. Find the speed as a... The force of tension is going this way. But DL, wow, that's crazy. It ended up being so easy, but this seems so hard. How did he find this voltage potential? Whoa. Damn. This is awesome. Torque again. Uniform torque. Oh, non-uniform lambda torque. Bro, that's a good problem. Damn, that's a good one. It is well known that a sphere may be replaced by an equivalent charge placed at a sphere's origin, but this is not so for other geometries. Consider a dielectric rod of length L and uniform charge Q. Distance from the origin is shown in the diagram. If the rod were replaced by a single point charge, find that point relative to the origin where the point charge would be such that the electric field from the rod is the same value. So, okay, so this is just an integral dE POS. You find it as it for the rod. Once you have it for the rod, you evaluate, you evaluate, you evaluate, you evaluate. Okay, so here is the electric field due to the rod. Okay, so now, or here it is. So now you want to say, yes. You just plug it into another Coulomb, a point source Coulomb for, no, a KQ over R squared. Okay, this is pretty good. I feel like I could do that. Use gas law to prove that the electric field inside a hollow uniformly charged cylinder of infinite length is zero everywhere. Oh, this is a good one to look at then. Here's this 3-step checklist. Can't be by circular symmetry. They're parallel, in fact. What are we looking at here? An infinite line of charge with a given linear charge density lambda is a distance d away from an infinite sheet of charge of given surface charge density, sigma. The line of charge is parallel to the sheet of charge, and a negative charge minus q of mass m is at rest a distance d away from the sheet of charge, okay? After the charge is released, find the speed of the charge when it hits the sheet. Okay, so yeah, so you basically do 2 Gauss's law. Then when you have, then you sum them together to get the E field as a function of X, or whatever. And then once you have the E field, um, the problem here is to recognize that you can't take. Okay, well, what you can do is you just integrate from d to 0, and then you get the delta, and then you can find the work done with minus q delta v, and then that's going to be equal to one half mv squared. Okay, this is like a pretty cool 2 Gauss law plus work energy to find a VF. All right, that's pretty cool. I'd say this is that's like one of those ones that I like doing, but maybe I should do the ones that I don't like doing, like Gauss's law, full, full. I hope there isn't a full treatment of Gauss's law because that shit is so confusing. I need to go find my notes where I wrote down the 3-step checklist. Or I think actually my friend wrote it down. Okay, referring to the diagram, a positive point charge Q of mass m is placed at rest at a dielectric uniform radius r q. A very small hollow shaft is carved. If the point charge is displaced slightly but is still at rest, it will be repelled through the shaft radially outward from the sphere. Find the speed of the point charge when it is a distance 4r from the center of the sphere. Find the speed of the point charge. Okay, so so basically this is another kinetic energy. What we're going to do is we're going to do a Gauss's law here. And we're going to have to do 2 delta V's. So we're going to find the delta V here and then the delta V here. And then we're going to find both of those works, add the works together, and then that's it. So he probably does exactly that. Yeah, so he does 2 line integrals. E inside, E outside, R to R. He did the Gauss's law here, plugs this in. So this is the first one. Then we just did you don't even need to do this one because this is literally just going to be well, you're going from a high voltage to a low voltage. So you're gonna have low minus high. This is gonna be negative delta. So it's gonna be minus KQ over R. Okay, I mean you could still do the line integral. Gauss law plus work energy, charge ejected from sphere, but dielectric. But the thing about that problem is needs 2 integrals trying to trick you. He's trying to see if you're gonna integrate the same potential function or the same electric field inside the dielectric sphere is going to be different than outside, and that's what he's tricking if you know. Okay, this is not going to be on there because it's like I don't think this is going to be on there. V squared. I'm going to bet that this thing is not really on there. But it could be. Can I do this? Maybe I should do one of these. A capacitor of plate area A and plate separation D is connected to a battery voltage V. A dielectric of constant K. No, this is not going to be on there. Yeah, I'm going to skip this one. There might be another one in the future that maybe, but this is a kappa dielectric. Skipping. Okay, this one's a possibility. No, wait, integral delta work. Shit. This is so new to me, dude. He didn't give us any time. He's like, what we cover in class today will be on the exam tomorrow. Okay, this is probably like a 5 out of 5. Need to at least look through a capacitor. So skipping that, this one, let's see. I'm gonna put it at the beginning. These are gonna be, uh, this is like a 4 out of 5. This isn't. I don't know. I should be more harsh, but I don't know. This one looks crazy. What was in here? The 5 out of 5. Oh yeah, it's like uh, very weird work energy. A solid dielectric sphere of radius r has a charge distribution that's weird. Find the total energy associated with the electric field. Okay, this is not on there. Energy density, no. Skip energy density. Okay, good. 7. A dielectric sphere with an inside hollow of radius Ri and an outer radius Ro is uniformly charged throughout its volume with a given charge density rho. Find the potential inside the sphere where the dielectric is. Find the potential inside the sphere where the dielectric is present as a function of the radial distance from its center. Okay, so we know that E is 0 in here, so that whatever, but that's not even important. You do a Gauss's law thing here, but then first you have to do first you say V at infinity is 0. Then you say, okay, here, what's the total, because you need to do a KQ over R. So you have this thing. So first you do the KQ over R, but then you have to do Gauss's law. And then to find E. So wait, we have rho. So first we're gonna get K times rho times 4/3 pi, and now it's going to be R O minus Ri. No, Ri. Wait, yeah, Ro minus Ri, or Ro cubed minus Ri cubed, and that's the total charge. Then you divide that by epsilon 0. Or KQ over R. This is the potential. And R is going to be RO. Okay, so this is like delta V1. And then delta V2. Let's see what if he does that. So, RI to R. Oh shit, I didn't. Okay, that's going to be my problem. I have to read the entire problem. So this is the zero potential. It's literally just a single integral. You find Gauss's law. Okay. Now, suddenly the dielectric sphere in part 2a becomes a solid conducting sphere, but with the same amount of total charge. Briefly describe what happens to the total charge of the sphere and the electric potential anywhere inside. Does it have surface charge density? Because I did a problem where it does, but that's only if there's a... I think probably it goes all to the very outside. Okay. Since everywhere inside, the potential will be constant. Let's close some of these. We can go back to them. If I have a charged conducting solid sphere, but there is a concentric hollow placed into it, on the inner the inner surface contacting the hollow will have 0 surface charge density, and all charge will be on outer surface. Right? That's actually super weird. Yeah, as long as the cavity contains no charge. That's actually super weird. Okay, this is a good one. With a part B. Part B is cool. I think I could do this. Briefly describe what happens. The potential of a sphere of radius r with charge q, kq over r. A dielectric sphere of radius r has a funny charge density. Find with an explicit calculation the total charge. Okay, so just remember that you have to integrate rho of r d vol, which is going to be 4 pi r squared, or the integral of 4 pi r squared rho of r dr. So he plugs this in here. We just got to remember that a shell, you're integrating an RDR. Okay, find the total electrostatic field energy everywhere due to the presence of the sphere. Okay, we're not doing this. Skipped part B. Skip part B because of energy density. The first part is like a 2 out of 5. Just integral. Oh, I'll probably want to do this one. This looks like in an otherwise solidly charged dielectric sphere of given uniform charge density rho and radius r, an offset spherical cavity has a non-conducting wire within the cavity and a charged bead. Bro, this drawing sucks. It's free to slide horizontally along, starting from rest frame. The time it takes for the charged bead to go from the center of the dielectric sphere horizontally out to the outside surface, the 3 o'clock position. Sometimes you gotta like ignore the wire has nothing to do with this. Fuck, these time ones suck ass. These time ones are so hard because I don't understand or what. I think the main thing is that you inside the hollow. Yeah. Okay, actually, I hate the drawing, but I think this is fine. You do. Yeah, k q over r squared twice because E out 0. So then you can find the E field at a point along the wire. You end up finding that it's uniform. Let's see. Wait, why isn't it uniform? I thought it's uniform. No, oh, no X. Yeah, R is constant. Yeah, no X. There it is. So it's uniform. So now here's the tricky next part. Now that you know the E field, you can find the potential difference. And with the potential difference, it's just going to be E times R. So that's the potential difference. So then you can find the work, which is going to be minus Q E R. With the work, you can get the velocity and the kinetic energy. The thing about the kinetic energy is really what you need is F equals ma. Yeah, if it's a time, you got to go straight to F equals ma. So it's like, so the F equals ma, A is equal to F equals ma, A is equal to F over, and this is gonna be QE. Okay, A is equal to QE over M. But then we know that AT, 1/2 AT squared is equal to R. And then we know that T, we don't know what T is. We know R and we know E and Q and M. So I think you just solve for 1/2 AT squared for T. Good. Okay. That's like not so bad. It's but how did he find the potential difference? Oh, he didn't. Okay, so the trick, okay, this is a potential and kinematics. The trick is to see that you don't need to find VF with delta V. Can go directly from the E field to finding the time because with E and constant we know force. All right. Okay, this looks a particle of mass m and charge q is okay is rotating in a horizontal circle as shown in the diagram. There's gravity in this problem. A uniform magnetic field. Okay, never mind. Skip magnetic field. Bro, if he gives us a problem about magnetic field, we're all cooked. Okay, a solid conducting sphere of charge q, a conducting sphere of charge q and radius r exists. How much work would it take an external applied force to construct another spherical shell of radius 2r and of negative charge minus q concentric around the original sphere at constant kinetic energy? Ah. Do I have those capacitance problems? I'm skipping this. This is like some energy density thing. I don't actually know what this is about, but I see E squared energy density. Skipping. Oh, okay. A dielectric sphere contains a positive charge density as rho, but a hollow has been created that has been filled with a negative charge of a different density rho prime. Find the value of the negative charge density in this cavity. That would mean a charge placed at the position shown. This is the position. Would mean a zero E field. Okay, so it's gonna be, yeah, POS solid cap. Oh, this is the, yeah. Okay. I need to redo this one. It's just a ton of freaking algebra. I could get this part, and then I know this is going to be k. First one is kq over r squared. Times the row. You fix the row. Wait, what? Um, this is the sphere. Q. If he finds Q, so then he does this thing. Do the solid. Do the cavity. And then where's the minus row part? This is like the best. This is like a 5 out of 5 POS problem. It's not hard, but like, let's see. Why do I think that it might be? You have this sphere, a sphere. This is minus rho. This is rho. This is P. E P equals 0. What is, this is rho prime. What is rho prime? So, and then the radius of this is obviously r over 2. This is r. This is r over 2. So E is equal to E of Sol plus E of Hall plus E minus. E Sol is going to be equal to K Q over R squared. Q is going to be equal to rho times 4/3 pi R cubed, which is equal to 4 rho pi R cubed over 3. Then divided by R squared, so this cancels like this. So this is the total charge, is 4 rho. Okay, so then so E sol is equal to K 4K rho pi R over 3. And it's going to be R hat. Okay, now E hollow. This is also going to be the same thing. It's going to be KQ over R squared. But here, R is equal to 3/2 R. No. Oh, yeah, 3/2 R. And Q is going to be equal to, 4/3 pi R over 2 squared cubed, pi R cubed times minus rho. Okay, so then, E of P of Hall is just, this thing and this thing. Okay. And then E of minus, or do we not just multiply that by 2? Pi K, or K pi R 1, 2, 3. Okay. So here I think he adds them together, right? That goes to here. This goes to there. Then he simplifies it. Then he says that they're equal. And then he finds. Okay. All right. Oh my gosh, it's already 10:37. Starting at the surface of a dielectric sphere, a charge plus Q. Starting at the surface of a dielectric sphere, a charge plus Q is fired with an initial velocity radially inward towards the center of the sphere. The sphere has uniform charge density with a radius r and total charge with Q. What is the minimum initial speed of the charge is necessary so that the charge could penetrate just to the center? All right, this is the classic work energy. You take the system to be Q. You do Gauss's law to find the E field. You find the delta V with a line integral because you need to do a line integral. And then you find the work, and then you know that QEF is 0, QEI is non-zero. Then you solve for VI. This is like a pretty normal. I feel like this isn't that bad. This is like find VI, Gauss law plus work energy. I would say this is like a 2 out of 5 on my priority. It's like pretty low because I feel like those ones I can do. All right, here we go. Weird torque problem. Dude, we're definitely getting a torque problem tomorrow, bro. All right, whatever. All right, from the diagram, find the torque on the rod. What am I even looking at here? Find the torque on the rod of length L and charge Q about the pivot point due to the infinitely long line of charge where lambda is given. Oh, this is a good one. I don't think we have a Gauss's law torque. Gauss law torque. Okay, so where's the pivot? Oh, but here's the interesting thing is this thing is like this. So we have to integrate. Okay, so I'm going to call this the origin. You do Gauss's law, you find what is it? Lambda over 2 pi epsilon x. So it falls off with a factor of 1 over x, right? Oh, this is actually a hard problem, dude. Oof. Oh, damn, bro. I love torque, and this is like a 5 out of 5. We got to do this one. This is actually helpful because I know maybe like what possible things could be on it. Oh, this is a classic one. But okay, here's what you have to. Okay, I should do this one again. This is 5 out of 5. There's not enough time, man. This one is good because. Are you given row? Yeah, okay. And Or wait, actually, here's what you do. You make another cylinder. You just do this. Okay, then you find it of R. So we're gonna have rho, E times rho R over 2 epsilon naught R hat. Okay, so now what we can do is we can say that E plus is equal to, rho over 2 epsilon naught times R, 3R over 4. Okay, then E minus is going to be equal to rho over 2 epsilon naught times R over 4 is equal to rho R over 8 epsilon naught. So this is a minus rho R hat. So then you just sum them. And you should get rho R over 4 epsilon naught R hat. So it's still net outward. Boom. All right. The hack with this one is don't go through all this crazy fraction stuff. Do one Gauss's law. You find what the E field is for a uniformly distributed dielectric solid cylinder. Then you just plug in the numbers. You just plug in the radius. You plug in this radius. Then for the small one, you plug in the other radius. And you just remember. You just kind of did. There's kind of a loss of the fact that, oh, well, which radius am I talking about? But it doesn't matter because even though you're using different radii, or like the center point that you're using for your E fields is different, the you've chosen the R's in such a way that the the points that you're talking about are talking about the same point. That's a terrible way to explain it, but it does make sense to me. Is like you have to have them intersect at a point. And I think that there's another good one. It's this, no, is it this one? It's that one about prove that the E field is uh which is the one where we prove with vectors work. Oh. Wait, what is this one? Let's just go through them all. That's the bead one. Where's the one that says do with vectors? I don't remember this one. Oh yeah, this one really good vector 1 5 out of 5. I'm gonna say it's a 5 out of 5 because uh need to know how to prove E constant in the standard sphere hollow. Standard offset sphere hollow. How many more do we have? Okay, there's not that many more. I'll probably go to bed. I don't know, I'll probably be pretty awake. All right, torque. Find the net horizontal force on the rod. Horizontal force on the rod. From the fixed source shown in the diagram. So we have a theta. So this is going to apply more force here. Force here. It's going to be. Oh, this is an interesting one actually. dq. What is dq going to be? So you're going to have r of s. R of s is going to be, s cos theta, s sine theta is the standard. But then so you have r of s. But then because what we need to integrate is e dq. E is going to be um this thing. So this is going to be, so I think that the vector is just going to be, because this, okay, yeah, this position is going to be like, what do we call it? Let's just call it minus x 0. No, just call it x. So then r vector is going to be s cos minus x s sine. So that's good. So what does that give me though? That gives me that the r, so it's gonna be k q over, and so now r itself is going, the norm is whatever that norm is, blah blah squared plus blah blah squared square rooted. But then so this is gonna be kq over r squared is equal to e. But we need the whole vector thing. So this needs to be over 3 times, r hat or r vec. So that's e. Now dq ds is going to equal to q over l. I'm assuming he just gives you q over l is equal to lambda. So so then but I think that's right. dq do lambda ds, and then we're just going to integrate, e dq or e lambda ds from minus L over 2 to L over 2. I'm pretty sure that's it. Yeah, he does some nasty thing here. Nasty, 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 nasty. All right, this is actually pretty straightforward. This isn't so bad. This is like a 2 out of 5. Not hard. Oh, but I should say what it is. It's a integral E dq. Oh, but find the horizontal force. Actually, see, you gotta pay attention. So I mean, I think that's just a matter of dropping, the vector. Okay, let's see what's up with this one. Ooh, I actually think this one's good. Find the final speed of the charged bead. All right, so basically, it's frictionless. So all you need to do is find the potential difference between here and here. And with the, yeah, and I don't think he, Okay, I don't think he will give you, hey, here's a hint, put V0 here. So I think that this is a good lesson that if you have one of these infinite things that's going to give you a diverging voltage, so that like if you set your potential at infinity to 0, the integral blows up, then set it for the initial spot. That's a good idea. Okay, so Gauss's law, you get whatever 1 over r, and then this is going to be, what are you given? Refer to the diagram, find the final speed on the charge. Okay, d plus l, d. So you're going to travel, wait, what? Oh, cos theta. Okay, you're going to travel l cos theta. So whatever the v is, if it's like 1 over r is the the E field scale. This scales like this for the infinite for the wire. So then I think you just have to integrate then. So you probably just have to integrate from d to uh, d plus l cos theta, and you're going to integrate e dot dl, but this is just going to be like e of r dr r hat, and then you're going to get, because it's just going to be radial, you're going to treat it as if it like went straight this way. Like the fact that it goes at this angle thing is just to like complicate and trick you, but it's frictionless. This thing doesn't even matter. It's 1 over r, right? Yeah, where's the Gauss's law? Here, yeah, 1 over r. That's what I thought. Okay, here's the integral stuff. And the end result is pretty nasty, but I think that this is like a 3 out of 5. 3 out of 5 work energy. Gauss law plus work energy. Or it's actually, yeah, it's work, yeah, it's uh I'm gonna bank on the fact that as long as I remember that capacitance is the charge on something over the voltage, the potential, that's as far as I'm gonna go with the capacitor stuff. An infinite line of charge with given charge density lambda is held fixed in a range such that it is perpendicular to a finite straight line length charge q l. Is this? What the fuck is this drawing? A range such that is perpendicular to a finite straight line of length charge q with length l is also fixed. The closest tip of the finite length of charge is distance 2l from the infinite line of charge. The mass of the finite length of charge given as m. Find the magnitude of the acceleration of the finite length after it is released. There's no need, quick and dirty Gauss's law. Oh, here we go. L. Oh, shit. Okay, so you find the Gauss's law that gives you the E field as a function of r, the radius. Okay, but then you have this length L lambda. It's a different lambda. It's lambda prime here. And you need to find the force. So then you're going to do a dq, which is just going to be like dr lambda dr. dq dr is equal to lambda. So dq equals lambda dr. And then you just integrate e dq from E is dependent on R. So you're talking about radius. So what you're going to want to do is from 2L to 3L. And then that's going to give you the force. This gives you the force. But now the magnitude of the acceleration is just going to be F over M. Integral, integral, integral. This is just the force, right? This dq dx. This is q over L. This is the lambda prime that I was talking about. R. He switches from R to X, but you could do DR and R. I mean, yeah, here's that thing. So he's gonna get ln X here, 3L. This is just 3/2. I actually love these infinite wire ones. These are really kind of nice. So now he just takes this and divides by the mass. Okay. I think the most important thing is to probably remember that every time you write down work energy, F equals ma, tau equals I alpha, you got to define what system you're talking about. That's really important. This is it's Gauss's law. It's probably like a 3 out of 5. It's Gauss law. Integrate E dq, plug into F equals ma. Oh, the POS. Okay, a positively charged dielectric sphere. Oh, this might be a good one. I don't know if I'm happy to see the hard ones or sad to see the hard one. I can't tell. Bruh. Okay. A positively charged dielectric sphere of given uniform charge density rho is shown in the diagram, but with an inner solid sphere of negative charge density called rho prime. Not the same magnitudes as possible. Find the charge density. Charge density? Actually, we know how to do that. Find the charge density of the negative sphere such that the electric field is 0 at a point 3. Oh, this is like an even harder one. It's actually not harder. It's, plus, plus, plus. I think I just did it. Didn't I just do this? No, I think I just looked at it. I don't think I actually did this one today. But yeah, it's just a bunch of weird fractions. I should probably do this. More POS. A dielectric sphere has a positive uniform rho, but the radius of the sphere is given as r. But within this sphere is constructed another dielectric of something called rho prime. This other sphere, also dielectric, has the center located at r over 2. Find the value of rho prime such that the electric field at the top of the sphere is only horizontal. Oh yeah, this is a good one. Oh, this is a good one. vectors and POS balancing row of dielectric sphere. This is all. This is probably even. This is 6F. What am I doing? These are both. I really should do those. Okay. We just gotta get through this. And I need to read this thing about biology for my quiz tomorrow, but it's not as important as this, man. Find the electric field vector, the position indicated in the diagram. All right, 2L, origin, y, integral dE, blah, 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 blah. Boring. I'll just write down. Ooh, these are my favorites. I love these. I hope that I get one of these tomorrow. There's so many problems. Oh, but this is the one with the hollow. Okay, wait. So what does that mean? That means we gotta find the E, and we're gonna have to add an R over 2. And then we can get the E of X, and then we can line integrate it. Or actually, you know what we could do? I think we could find it for the inside, and then since this is always outside, you could actually just use KQ over R for these. I actually kind of want to try that. I don't know if that's true. Can you do that? Because he probably didn't do that, but I feel like you can just do that. He integrates from R to 0. Why did he integrate from R to 0? Why didn't he integrate? Oh, wait. It's just, oh, it's shot in. Okay. It's shot in. That's fine. Um, are you allowed to do this? Yeah, is that right? He didn't use Gauss's law to find the. Which one is this? 91. Work energy 32. There's nothing said about it, but this seems off. Hold on. The point is, do I think I could find the E field fast? Okay, so let me do it this way. All right, I want to find just the E field inside on the x-axis. So we have a circle, we have a hollow. Right, so um, this is going to be, so for E of x, less than 0. This one is going to be the electric field is equal to KQ. This is going to be, rho times 4/3 pi plus A. And then this is R hat. But it's going to be minus rho. And then E plus is going to just be equal to, what did I just say? I just did the thing. Rho R over 3 epsilon. Rho R over 3 epsilon naught R hat. So then here, we're going to add these two together. So we're going to get rho R over 3 epsilon naught. Actually, wait. A, this is going to be R over 2. What am I doing? R over 2 cubed. But this needs to be x. What am I wasting time on? Cos theta plus x. X minus r cos theta. X minus r cos theta? Why is it minus? No, because this is going to be negative. Yeah. Need to always do these vectors, bro. Okay, I don't think that I have really much of a problem with that. Let's look at 2. Man, these ones, the algebra just sucks. I mean, look at this. Square root 5, 15. Consider the dielectric sphere charged throughout with an offset spherical cavity. Find the magnitude of the electric field vector I think this is actually hard. Because, like, what is all this stuff? Okay, so the magnitude of the solid's easy. This one's also fine. When they're both on the outside, it's not that bad. But then, okay, this is the magnitude, but then he has to do the cosi for this part, and the sine I, which is going to point in j hat. So wait, hold on. The cos, this is theta, so the cos is the j hat, right? What? I think he flipped that around. I'm pretty sure that the cos. Okay. Find the position relative to the origin where the entire charge of the rod Q could be placed at a single point charge, such that the electric field at a horizontal distance find the position relative to the origin where the entire charge of the rod Q could be placed as a single point charge such that the electric field at a horizontal distance to the right of the rod. Okay, so first we're going to find the E field here. Then we're going to use that same Q. What did he find? He found the E field. Then a point charge. We need to. Okay. Why is this -1 here? The point charge. We give a field of. Okay. This is a good one. Ooh, I like these ones. Okay, given a circular ring of charge Q and a radius A, find the point along its axis where a charge placed at that point would have a. No, actually, I hate this one, bro. Okay, so first we find maximum acceleration. That means maximum force, right? So we don't actually have to find the force. We could just find the maximum E field. So we're going to do integral dE POS, which actually for the ring is super easy. I don't even think you have to integrate. So then, I mean, you do, but it's like really easy. Yeah, because you just pull out everything that's not. Oh yeah, he doesn't even. Yeah, it's just KQ x a squared plus x squared. So here's the E field. Then once you have the E field, you take the derivative with respect to x, right? Ugh, actually, I don't make me take a nasty derivative. I hope I don't get that one, man. Because I don't think I know how to take the derivative of this. Yeah, so he says that, okay, this kx, or the kq has no impact. So we're just going to take only the important parts. Okay, and then he does a product rule plus 2x times minus 3 halves. That's going to be a 1/2, I think. Okay. All right, so he just raises it to the top and does a product rule, which is fine. I think that's not the worst thing in the world. That's like a 3 out of 5. An electron orbits a proton in a given circular radius r. How much work would it take an applied force to move the electron from its orbit to infinity, where at infinity its kinetic energy would be 0? Um, well, what's that? E. What is that? 1/2 ke squared over r. So in this case, he didn't give you. It didn't give us the mv squared thing. V squared over r. That's what it. That's what it is. All right, I'm gonna have to go to bed and just hope for the best. Bro, this exam, man. Two conducting concentric spherical shells of radius r inside and r outside have equal and opposite charges. The inner sphere remains fixed and never changes, but the outer sphere, however, is flexible like a balloon. Whoa, wait. Two conducting concentric spherical shells. Mu E. Okay, energy density. No way. Whoa. What are we looking at here? Use a full informal vector treatment of the coordinate system given. Find the E field vector of the half ring of a charge of a given. Find the E field vector of the half ring of charge of a given linear charge system lambda at the indicated point in the diagram. Is this the point? What is this line? What is this, bro? I swear his diagrams are so ridiculous, man. He's like, this is the diagram, bro. My teacher, he was like, I've taken all the drawing classes. Are you sure? Are you fucking sure, bro? I don't believe him. But I think this is the point. No, is it the point? I can't tell. Oh, here's the point. Okay, this is okay. I one. Oh no, A. Oh, okay. Oh wait, what? Oh, that's a good POS problem, dude. AI plus AJ. Okay, so we do this. We have this ring here. Okay, then we go here, here. So this is going to be AA. This is radius A. This is a half circle of charge. And there's lambda on this thing. E P is E of P equals what? So we're gonna have a DQ. But does he leave the integral? Okay, good. Okay, I actually, now that I'm thinking about it, it's like it would be nasty, but it's like not that hard to do. Bro, I'm crashing so hard. Find the maximum angle of separation. Oh, another one of these. Yeah, okay. I'm glad I saw it. This is the same problem, right? That was the one I was crashing out on in oh, not the E ring integral. He likes these. Do I think I could do it tomorrow? Maybe. This one was tripping me out though. Okay. I don't know why he does the. This is for the center surf. Where's V surface? Oh, this is just V, and then he just. Wait, hold on. Oh, this is actually a good one. I'm too tired to do this. All right. Thin rod. Held fixed in a vertical position is shown. Uh, Vertically above the rod, initial distance d, a positive charge of mass m is projected downward. Find the closest distance it gets. There's no gravity. So VF equals 0. You take the system just as Q, then the work done okay, yeah, this is integral dv. He doesn't actually, I haven't seen that many integral dv. They're not that hard, but I haven't seen a lot of them. And then the algebra just gets really nasty. Just get to the surface. Say that we wish to get a positive charge not just to reach the surface of a nucleus, but instead to go all the way to its center. To model this problem, we pretend the nucleus is a dielectric sphere, radius r, and total charge plus q with uniform charge density. Say that the positive charge plus q is starting infinitely far away. How much more would the initial kinetic energy of the charge starting at infinity have to be such that it doesn't just reach the surface, but just goes right to the center? In other words, find the work to go from here to here. Find the ratio of kinetic energy? Two conducting spheres are separated by a large. Find the potential of the surface of the charge sphere relative to potential of infinity. Why does this line integral look nasty? Oh. Yeah, I think I tried this one. Maybe I didn't. I definitely saw it before though. Okay, that's it. No more problems tonight.